Hi guys, today we are going to discuss another very important topic, that is Klystron. So first let me tell you about the history of Klystron. In 1937, American engineers Russell and Sigurd Varian developed Klystrons. And in our today's lecture we will study about two-cavity Klystron amplifier. So first let's define what is Klystron. Klystrons are special type of vacuum tubes that find applications as amplifier and oscillators at microwave frequencies. Its principle of operation is velocity modulation. Here velocity modulation means that the modification of velocity of a stream of electrons by importing alternate acceleration and deceleration to the electrons in such a way that they are caused to bunch together, with the result that each bunch causes a cycle of current as it passes an output electrode. Thus, the device used for the amplifying microwave signals is known as two-cavity klystron. Klystrons are majorly classified as two-cavity klystrons and reflex klystron. Here in this lecture we will discuss the construction and working of the two-cavity klystron amplifier. First we will discuss the construction of two-cavity klystron amplifier, then operating principle, then working, and at the end we will discuss the applications of two-cavity klystron amplifier. So first let's discuss the construction of the two-cavity klystron amplifier. The figure below represents the structure of two-cavity klystron. As we can see, the above figure consists of two cavities, namely buncher cavity and catcher cavity. The RF signal to be amplified is provided at the buncher cavity. The electron gun comprises cathode, heating element and anode. The electron beam is produced by the cathode and making use of heating element, and the high positive potential at the anode provides required acceleration to the electron beam initially. The region between two cavities is known as drift space, which you can see in the diagram or the structure of the two-cavity klystron amplifier. To allow focused propagation of electron beam inside the tube, an external electromagnetic winding is used that generates a longitudinal magnetic field. This is done in order to prevent the spreading of beam inside the tube. The amplified RF signal is achieved at the catcher cavity. Also, a collector is present near the second cavity that collects the electron bunch, which you can see in the diagram. And now, before going to discuss the working of two-cavity klystron amplifier, let's discuss the operating principle of klystron. So basically the operating principle of klystron is such that the kinetic energy of moving electron beam is utilized for amplifying and generating microwave signals. As we have already discussed in the introduction that klystron is based on the principle of velocity modulation. Thus, two-cavity klystron amplifier utilizes the kinetic energy of moving electron beam and signal amplification. The variation in the velocity of electron while moving inside the tube is known as velocity modulation. This velocity modulation permits bunching of electrons while propagation. So the combined energy of the bunch electron is transferred at the output, thereby providing an amplified signal at the catcher cavity. And now we will discuss the working of two-cavity klystron amplifier. Initially, electrons are emitted from the electron gun, and the anode present in the structure provides the desired acceleration to the beam. In the first case, in the absence of RF input, the electron will tend to move with their respective uniform velocity to reach the catcher cavity and gets collected at the collector. And now if we apply external RF signal at the input of the buncher cavity, then this causes the generation of local electric field inside the tube. This electric field causes the bunching of electron as the field applies acceleration and deceleration to the moving electron according to the polarity of the signal by which the field is generated. Basically, the reason for causing acceleration and deceleration is that when the direction of movement of electron is opposite to the direction of the field, then in this case the electrons experience a decrease in their moving velocity. And in the second case, if the generated electric field and the direction of movement of electron are the same, then in this case the electron experience increase in velocity of their movement. And now let us understand in detail how this increase and decrease in velocity causes bunching of electrons. In the first case, when negative half of the RF signal is provided as input to the buncher cavity, then the moving electrons experience a repulsive force due to presence of the negative charge at the entering plate of the buncher cavity, which you can see in the diagram. Or we can say that due to negative half of the input, the generated field will be in direction opposite to the direction of the movement of electrons. So because of the opposition offered by the field, the moving velocity of electrons get reduced. In the second case, when positive half of the RF signal is provided, then the positive potential at the first plate of the cavity applies attractive force to the moving electrons. More simply, for the positive half cycle of the input, the generated electric field will be in direction similar to the direction of electron movement, which you can see in the diagram. So this leads to an increase in the moving velocity of the electrons. Thus, combinedly, when we consider both the cases, then the electrons that were emitted earlier by the gun will be decelerated, while the electrons emitted later will be accelerated. Thus, all the electrons, while moving with different velocities, get bunched in a drift space. This change in the velocity of electrons while moving due to RF input is known as velocity modulation, which we have already discussed. Once the electron bunching is done, then the catcher cavity present at the another end of the tube absorbs the beam energy. It is to be noted that to find the position of the catcher cavity, transit time of the bunches must be considered. This is so because the catcher cavity must be present at the sufficient distance from the buncher cavity so that bunching can be attained in the drift space. Further, once the energy is transmitted to the catcher cavity, then electrons, now with low energy, gets collected at the collector. And now we will discuss the Applegate diagram of the two-cavity klystron amplifier. The figure below shows the Applegate diagram that represents the bunching of electrons moving with different velocities. The electron traveling inside the tube under the absence of external fields acts as the bunching center. The electrons moving due to influence of the positive half cycle of the signal reaches faster, while the movement due to the negative half cycle is retarded. Thus, the figure represents the bunching process at the center point at a specific distance inside the tube. and at the end we will discuss the applications of two-cavity klystron amplifier. The two-cavity klystron amplifier find application in satellite communications, UHF TV transmitters, as well as radar systems, wideband high-power communications, and troposphere scatter transmitters, etc. So this was our detailed lecture on two-cavity klystron amplifier. Hope you guys like it. See you guys in our upcoming lectures. Thank you very much.